Hi. So this is College Physics 2. My name's Guy O'Lakin. Uh, what we're going to do today is, well, I wasn't planning to spend a ton of time on the syllabus, but more than half the class is from other College Physics 1 classes. So I think maybe I'll go through that sort of carefully. Um, that'll probably take most or half of the class. And then the rest of the class, we'll start talking about the first topic. So we will get to some physics stuff today. Um, this is a 4-credit class. The lecture is worth 3 credits. And so as far as like expected time commitment for this class, I think that's probably worth mentioning. A 3-credit class, this isn't like a new thing that I'm making up or anything. It's sort of like standard. You can look it up on the internet. They'll tell you the same thing. Like you can sort of expect 2 to 3 hours of outside work for every hour of credit of in class. So for 3 credits, that's 6 to 9 hours of work a week that you owe me. You owe me that time, and I'm going to collect. No, but um, I think probably you could get by on the low side of that, but that's the right ballpark. Okay, so like if you don't have that amount of time to devote outside of class, then this probably just isn't the right time. Like maybe you could get through, but it's sort of taking a risk. So I would recommend right from the start, um, go to your day planner or whatever, block out, find the, say, 6 hours a week that you're going to have, that you're going to put into studying here. And just right from the start, uh, spend, spend Wednesday from this to this and Saturday from this to this working on this class. And I think if you do that, you'll find that understanding these topics isn't that hard. You'll have time to do a lot of repetitions on the practice problems, and this will be a really low stress, fun class. Um, there are 2 different lectures. This is the day lecture. There's also a night lecture. Here are the times and room numbers for those. Uh, that, like, it's worth paying attention to when the other one is, the night class is. Because if you ever can't make it to your lab or your lecture, especially like on exams, it would be important. If you ever can't make it to your exam, but you can make it to the night exam instead, or if you just, works better for your schedule or whatever, you're welcome to go to the other class instead. They're pretty interchangeable. And it's no extra effort for me to, if you take your exams with the night class or the day class. So you always have 2 options for whenever to take tests. And you always have 3 options for when to do your lab. If you can't make it to your lab at the scheduled time one week, just feel free to show up to a different lab. My office, this is wrong. My office is 2302 upstairs. So I guess I'll get that corrected, but my office is S2302. It's just right up at the, like, on this side of the hall, all the way up at the top of the stairs. And the best way to get a hold of me usually is email. If I don't get back to you, it's just a email management system problem. I'm still improving at that as I age, but so there might be times when you send me an email and you don't hear back from me in a day or something, and that just means I missed it, and now there's more emails on top, and I'll never remember that you sent me an email again. So just send me another email and say, remind me that I got the first one, and then I'll be embarrassed about it, and I'll get right back to you. Okay. My office hours this semester, I'm planning on only doing them Monday and Wednesday. So Monday from 3 to 6, Wednesday from 4 to 6. Um, for the people who haven't had my class before, um, I do those in, I don't know what rooms are open yet, but either in a classroom or in a lab. So there's room for you to just sit and work on problems. Uh, and so if you have the time, if you can make it to those, it works really well as like a study hall because other students are around that you can work with, and I'm around if you have questions. Um, so it's been my experience that the people who have uh, consistently taken advantage of those, like say every week come to Wednesday office hours, uh, do considerably, like statistically, do much better in the class than the people who don't do it. You know, I mean, that's not a very carefully controlled like statistical study, but I think it does help a lot. Um, it helps to work with other people, and that's a easy way to work with other people, like especially if you don't have other friends in the class. And it's nice to be able to work on stuff, and then I'm right there if you, oh, like I don't know what to do here, and I can just answer the question right then. Um, if you can't make it to office hours, you want to meet outside of office hours, I can do that, but just please, let's schedule a time. Um, I'd rather not, you know, otherwise the alternative is like people just end up sort of dropping by, but since there are 100 people in all my classes, that ends up being like every 37 minutes somebody comes to my office, and it's just hard to get work done. So I'd rather if you would just send me an email, schedule a time, and we can meet outside of office hours. Okay. Um, the materials required, you need a scientific calculator that has trig functions on it. And there's no required textbook for this class. Sometimes people ask for recommended textbooks, and I will give you a recommended textbook, but really my main recommendation is just trust that there's going to be enough information coming from the lectures and from the practice problems. I do it that way. Two reasons. Like the smaller reason is, you know, it saves some money because textbooks are expensive. But the bigger reason is I just want to be as clear as I can about what material you're you know, responsible for in this class. So instead of having 200 pages of stuff that you're sort of vaguely responsible for, the stuff I say in class, I expect you to, you know, go over your class notes more than once, understand that stuff really well, remember what topic follows what topic. And then I'll give you a set of practice problems, and I expect you to understand the skills in those practice problems really well. And that's all. So since, you know, my thinking is, since I'm sort of limiting the amount of material you're responsible for, I can expect you to understand what I do give you a little more than, you know, in a little more detail than, like, say, a biology class where you're responsible for 250 pages of textbook stuff. So please don't think about it as like, you know, there's that much less material, so the class is like that much less work. It's it's more like a priority that like I just like you to focus that much more on the stuff I give you and don't worry about outside stuff. The prerequisites are college algebra and physics 1110, that's college physics 1. Although this is sort of a funny thing, like these classes are so separate. I think someone could probably, like a fairly good student who was willing to work pretty hard, I don't think would have too much trouble taking physics 2 without physics 1. They're pretty separate topics. Physics 1, you know, is about forces and free body diagrams and kinematics, the motions of objects that you're used to in your everyday experience, balls and rocks and whatever. Physics 2 is about a lot of stuff that you don't have as much intuition with. Thermodynamics, the transfer of heat from one object to another, the behavior of gases, and then most of the semester has to do with electricity and magnetism. Well, I guess before I go into those topics, the website for the class is D2L. If there's anybody who is new to Normandale or hasn't set up a D2L account yet, come talk to me after class and we'll just make sure you can get set up with that, because you'll want to check the D2L page like every day, you know, just check the news feed once a day, see if there's anything new that I've posted. If I post anything new, it'll say something in the news and it'll say where to find it. One thing that will be on D2L that'll be helpful to everybody sometimes, I think, is so, you know, instead of writing on the whiteboard or the chalkboard here, I'm going to be writing on the screen, you know, like this. So that's my whiteboard. But the benefit is I'm also recording this as a video file, and I'll record the document as a PDF, and those will be posted on D2L. So if you miss class, it's really easy to catch up. Just go to D2L, print out the PDF of the notes, and then follow along on those as you watch the video, and it's just like being in class. Yes? Yes, and YouTube too, because for people who use, I think, Chrome, and people who use whatever Unix uses as a, and also for people who use Apple's, the streaming from D2L doesn't work very well. So anyways, those video files will also be on YouTube. And on D2L, I'll post where to find those. So if your browser doesn't show the videos, the most common thing that happens is you'll hear me talking, but you won't see any kind of video. Then just go, you know, print out the PDF and then watch the video on YouTube. Also, I don't take attendance in this class, so anybody who, you know, I mean, I know everybody has a lot of things going on, and if it works better for you to not come to class and just watch the videos, go through the class like sort of as a hybrid or an online class, that's fine with me. I do think there are benefits to being in class. Pretty much, like, on average, once a class period, I'll take a break from lecture and have you guys work on a problem together. And I think being in class for that is helpful. But I've had a lot of people go through this class successfully without, you know, get A's in this class and good grades in this class without coming to class. And I know it can be done. And so if that works best for you, feel free to do it. It will hurt my feelings, but it won't affect your grade. I'm really good at separating that. I've dealt with a lot of pain in my life. So, any questions so far? Okay, the topics in this class, we're going to start by talking about harmonic motion, so that's vibrations, and then vibrations are connected to waves, and I'll talk about how that connection works. Then I'll go into what I'm calling here temperature and kinetic theory. Essentially, that's the behavior of gases using the ideal gas law, and heat transfer in gases. And then we'll talk about thermodynamics, which is the biggest part of thermodynamics is how to convert thermal energy into mechanical energy. So last semester, we talked about mechanical energy, kinetic energy, and potential energy. Essentially, the whole Industrial Revolution came about as people started to figure out how to use coal fires to create mechanical energy. And so along with that went steam trains, steam engines, and the powering of machines powered by fire. So, and actually, so the Industrial Revolution was a long time ago, but these same ideas are still used in modern power plants. Like, for example, a steam engine, you think of like a steam train, but modern nuclear power plants still are steam engines. It's just that they don't use somebody isn't shoveling coal into a fire. They're using nuclear reactions to heat up the water, and you get the water really hot that way. But the essential ideas here are still useful. Okay, so once we've talked about waves, the gas laws, and thermodynamics, then we're going to move on to the bulk of this class. Probably more than half of this class is talking about electricity and magnetism. There's a cool connection between magnetic fields and electricity. And I mean, I say cool, it's cool when you see it happen. But in fact, you could say that if there wasn't that, the connection between electricity and magnetism, you could say it, and it's correct. You can say lots of things, but not all those things are correct. But this would be correct. All the life on Earth is possible because of the connection between electricity and magnetism. And I say that because electromagnetic waves, which happen because of this connection between electricity and magnetism, are the way that we get energy from the sun through empty space. And without energy from the sun, there's all life depends on that. So so this connection between electricity and magnetism is pretty fundamental, and it's a fundamental area of study in physics. Once we're done with electricity and magnetism, the last topic that we'll discuss is optics. And we will get into some of that, and how much we get into just sort of depends on how quickly we go through the other stuff. Any questions about any of the topics in this class? Okay, the grading for this class is most likely, it's essentially going to be a straight scale. A's are 92 and above, which makes people grumble, but too bad. Oh, and the B's only go up to 89, so of course if you get a 90 or a 91, you get an incomplete in the class. That's pretty obvious. No, this should go up to 91 or 92 or whatever. If I feel like the scores are lower than I think they should be, because my tests were harder than I meant them to be or whatever, I might relax these cutoffs a little bit. I ended up doing that last semester a little bit. I think all of these grade cutoffs got bumped down 2% about. But for the most part, you can count on this being pretty good judge of where you are in the class as you go, I guarantee, sometimes, especially in physics and engineering, it's not super uncommon for the class average to be 60% and the A's to start at 68% or something. I guarantee that's not going to happen, so. And one reason that the class is that way is because I think the exams, and my intention is for exams to be pretty straightforward applications of the stuff that you've done in the practice problems. And so I don't think anyone is, for the most part, too surprised about what's on the tests. And I also never intend for the tests to be real like races against the clock. Although, you know, sometimes I'll miss a little bit on that one, and people will have to rush a little bit to finish. But I usually design the tests to be about an hour-long exam, and you have 80 minutes to take it. So, like, my goal is to have about half of the people in the class gone within an hour. The smellier ones. And then, you know, everyone else can concentrate better for the last 20 minutes. So the grade breakdown is going to be, the bulk of it is going to be exams. There are 5 total exams. That makes up 80% of your grade. I know that, like, people who haven't taken my class before, like, that makes them a little nervous. I know some people would rather have a bigger percentage based on other stuff. Like I said, I mean, I do it that way because exams are easier for me to control. I don't know what to say. So if you don't like that, I'm sorry. That's how it's going to be. But I do make an effort, like I said, to make the exams not horribly stressful, and there are 5 of them, so you don't have any one exam that's like really, you know, your whole grade is super dependent on. Also, the first 4 exams, I have a makeup exam where you have the choice of making up any one of those 4 with like a new version of the exam that you choose. So if you do bomb one of those first 4 exams, you can have a second crack at it. That is assuming that you've made it to all the exams. If you don't, like if you miss an exam, the makeup policy is then you use your makeup exam to make up the one that you missed. So it's sort of an incentive to come, you know, to be here for all the exams. If you miss more than one exam, then that's sort of a problem with that makeup policy. You know, like you can miss one, take it during the makeup period, and it doesn't affect your grade at all. But if you miss a second one, obviously, then you're going to have a 0 on one of those exams. So, you know, I can maybe, you know, we should talk about it if you have to miss an exam, but, and maybe I can make exceptions, but essentially, like, you should look at when the list of dates for these exams and make sure that you can make it on those days. If you can't make it to a bunch of those, this might not just be a time that you can take this class. Remember, by the way, that you have both of these 2 options. So, like, if you can't make it to exam 3 on April 10th, but you can make it to the night class the night before, that's fine. You don't have to tell me beforehand. You can just show up to whichever one works out better for you. They're always going to be 2 different versions of the exam, so it doesn't, you know, it's not like a concern about someone in this class taking the test early or anything like that. So feel free to use that. Any questions about the makeup policy or anything about the exams? Oh, one thing, they're not exactly all weighted the same. The first 4 are all weighted the same. They're each worth 15% of your grade. And then the cumulative final exam is worth 20% of your grade. So it's worth a little more, but not too much more. Okay, so those are all the dates. here's a little section on what I said at the beginning. I really feel that if you right from the start, like somebody who's taken Physics 1 and taken college algebra and right from the start diligently spends 6 or more hours a week getting ready for this class, I really think I can promise you'll do well in the class. But my lawyer said I shouldn't do that. But really, like, you'll do well in the class if you do that. And if you, like, after the lecture, you go and spend your next couple hours of studying, going over that lecture I just went over, make sure you understand all the concepts right away, and then the next time you go to it, start working through the practice problems. And I think you'll find this class to be a good experience, not a lot of nightmares and stuff the night before, night sweats, night terrors, that kind of stuff. Okay, cheating. Really the only way cheating can come up with it in this class is copying on exams. One thing that's, we have a small enough class here that we can stay separate, and there's not as much of a problem as when people are a seat apart, but please don't, please be disciplined about not looking at the exam next to you on exams. As far as, maybe I missed, I think there should be a part on assignments here. Here we go. So I skipped this section, but there are 2 types of problems that I'll give you. The first type is called the practice problems. And those are the ones that are going to be very similar to the exam questions. And I'll give you full solutions for those. So those are like study aids. And the way to get ready for exams after you've carefully gone through the lectures and everything is just to, without looking at the solutions, work through those practice problems, then compare your answer to the solutions. And if you want to, I think it's really useful, and I'd be happy to do this, bring your finished practice problem work into office hours, and I'd be happy to go through and say, like, okay, everything you did here is fine. This deviation you made here is fine, but this way, I really want you to do it the way I did it on the solutions, and here's why. And so I'd be happy to do that, and I think it helps to do that if you want to. Okay, so those practice problems are a tool for studying for the exam. Then I'll also give problem sets. Those are not as related to the exams, but those are going to be more involved problems, just like 1 or 2 problems. I'll give you a week to work on it. Then they'll be due during your lab period. And the way we'll grade them is you'll bring your completed work into your lab, and then just one by one during lab, I'll pull people out into the back room and just have you walk me through how you did it, sort of step by step. And we might not go through the whole thing, but it's a way for me to first make sure that you've sort of internalized the steps of how to do this. And that's what the problem set is going to be graded based on. And second, it's a way for me to give like immediate feedback. I don't think, like, writing feedback on problem sets, I don't think works as well, because for one thing, if I get behind in grading, you don't get it until way after you've done the assignment. And then second, even if I write good notes on it, which is kind of a big if, still, like, a lot of times people don't look too closely at the feedback. So I think that it just works better, like, you go through it and I say, okay, right here, I want you to do this. So that's why, even though like this way of grading problem sets seems a little cumbersome, I think it has a couple nice features to it. And I would always be happy and encourage you to work together on the problem sets. As long as you get to the point where you can explain what you're doing and you understand how to do it, I'm happy with you working together. I think it's a good habit to get into for any science class to work together on stuff. So. I will also, so the last, probably the last week of lab in this class, I'll leave open for people to redo problem sets if you want. So like if you got a score that you didn't like on one of the problem sets, you can just redo it, come in, discuss it again, and improve your grade. There won't be very many of these problem sets throughout the semester, hopefully like 3 total. Any questions about that? Okay, other general policies and comments. Like I said, I don't take attendance, so feel free to, you know, if coming to class works best, I mean, I think it's a good idea, but if the videos and the lecture notes online work fine for you, then feel free to do that too. And remember that everything is posted on D2L, so just get in the habit of going to D2L regularly. Okay, any questions about anything on the? Yep.
Happen to know when the finalists? 11 on Tuesday at 11.
Ah, thank you. And I know that that is always subject to change until the last week, but they don't change it very often. I have had it changed. I don't know how many finals. I've been here 5.5 years. And so how many finals is that? It's impossible to calculate. But let's say 25 finals. Okay? I've given 25 finals, and one time I've had them change it. So your odds are pretty good that that'll be the right one. Any other questions? And I think the night final is always on the first Monday, like the first day of finals at 6 p.m. So, you know, you could take the final then too. All right. So the first thing that we're going to talk about in the list of topics for this class, I said that the first topic was waves. I'm actually going to break waves up into 2 things. The first part is harmonic motion, and then the second part is waves. So I'm going to start with harmonic motion. You can think of that as being equivalent to vibrations. And harmonic motion is when an object periodically retraces its steps back and forth. So here's an example of harmonic motion and an example of a periodic motion of an object that isn't harmonic motion. So harmonic motion, the example that we're going to use the most is a spring connected to like a wall, connected to a mass that can move back and forth. And if you pull this mass to the right and let go of it, it'll move back and forth, going along the path in one direction and then along that same path in the opposite direction. Okay? So that's harmonic motion. On the other hand, a train so that's like supposed to be a top view of a train going around a circular path. That's a periodic motion, okay? Like every minute and a half or whatever, it comes back to the same spot and repeats. But it's not harmonic motion because it's not going backward and forward along that path. It's only going in one direction. Okay. So some examples of harmonic motion. Are a mass on a spring. Probably more than half of our calculations, definitely more than half of our calculations will just involve this one simple setup. A pendulum. And then the last one, this is supposed to sort of lead into the next thing I want to discuss is a speaker cone. So when a musical note is played on a speaker, the cone in the speaker is just oscillating back and forth, okay? And so it's in harmonic motion when it does that. And so that sort of leads into the question, why study harmonic motion? There are a lot of types of motion, and only a very small number of those are singled out in physics classes for study. So what is it about harmonic motion that makes it, more useful than this motion? Yeah. Like we could study that motion, like what? It would be more complicated, you're right. But that's not really the only reason that we don't study that motion, and we do study harmonic motion. So there are kind of two reasons that it's reasonable to study harmonic motion. The first one is harmonic motion has engineering applications. So there are a lot of times in engineered structures where something might be prone to harmonic motion and you want to reduce those vibrations, like bridges, buildings, or I shouldn't say, sometimes you don't actually want to eliminate that, like in skyscrapers, in places that have earthquakes and things, like in Japan, the ability to vibrate is built into the design. But you do need to understand the modes of vibration that are possible in designing things, or else when vibrations occur, they can do a lot of damage. Okay, so in a lot of civil engineering applications, understanding vibrations is important. But that's for engineers. That's not for physicists. Physicists don't really care too much about like real world structures and things. But there's another reason that vibrations is an important area of study, and that is that vibrations cause waves, and waves cause vibrations. So I'd just make that a little double-headed arrow there. And I was sort of hinting at that with my example of the speaker cone. So a speaker cone is something that we can study in this section. We're going to be, we could talk about the harmonic motion of the speaker cone moving back and forth. That's not a wave, but when it vibrates back and forth, it makes air molecules near it vibrate back and forth. And that makes the next set of air molecules vibrate back and forth. And little by little, these vibrations are propagated through air. Okay, can you sort of picture how that's happening? And that propagation of vibrations is a sound wave. And so the vibrations of the speaker cone produce a sound wave. And then how does the sound wave produce vibrations? Well, when that sound wave gets to the air molecules next to those little bones in your ear, whatever those are called. What are those called? The ear bones? Thank you. When it gets to the ear bones, the air molecules vibrating make those vibrate, and that's what your brain perceives as sound. And so it's this interchange of vibrations of objects, waves in a medium, and then vibrations again that lets us hear something that happened at a distance. And so there's this connection in physics between vibrations and waves. Waves are a really important topic in physics. For one reason, electromagnetic waves that I mentioned before, the reason that there's any life anywhere in the solar system, that's a pretty good reason to study waves. So I don't know. Talk to me later if you need more reasons. You're pretty, if you need more reasons than all life on Earth, like you're pretty picky. Mathematically, we'll focus on one simple type of harmonic motion called simple harmonic motion. But simple harmonic motion actually has a very specific mathematical meaning. Harmonic motion. But simple harmonic motion is motion where the position of the object as a function of time is represented by this function. And this function has sort of a simple form. That's where the name comes from. A times the cosine of omega t. And we'll talk about the details of what this equation means, what happens if you change these values. This A is called the amplitude. This omega, it's a Greek letter, is called the angular frequency. All right, well, let's talk about the first example of simple harmonic motion, the mass spring system. Let's say that the mass of this cart is m, and notice that another thing that's going to affect the behavior of this system, like how quickly it moves back and forth, is how stiff this spring is. Like if you just think physically about this, a really flimsy spring, a spring that's really easy to compress or stretch, is going to have a harder time fighting against the inertia of this once it gets rolling. And so it's going to take longer for it to turn it around. And so if this spring is really flimsy, it's going to be a long, slow oscillation, okay? If this spring is really stiff, like imagine it's made out of thick steel, if you flick it with your finger, it's going to vibrate just really, really fast like this. So a higher stiffness of this spring means faster oscillation. Lower stiffness means slower oscillation. How do you represent the stiffness of a spring? Remember, we talked about this briefly. K. Yeah, K. Okay, so yeah, K is called the spring constant or the stiffness. And with these two parameters, say that you pull the mass to the right to this position, a distance a from the resting position. The oscillation is going to, so zero, the zero here for this number line is going to be the resting position. You're going to stretch it out, stretch the spring out, and start it at this value positive A. Okay? When you let go, it's going to move back this direction. And it turns out that it's going to keep going this direction until it gets exactly to negative A. So it gets exactly A on the other side of the resting length. So there's this symmetry in the motion. And then it'll go back to here, and it'll just keep repeating this motion between the two values, positive A and negative A, where 0 is that resting position. In real life, if you did this, there'd be some friction, you'd lose some energy, and so each motion, it would come a little short of negative A, then a little shorter of positive A, then a little shorter of negative A. Little by little, it would lose all its energy until it was at rest. But we're going to assume that this is an ideal thing, and actually, we'll see that as long as you're not trying to evaluate it over a really long amount of time, this can give you pretty good results. So we're going to assume that it would just go forever. Okay, so this is the motion. Take a minute and plot this out. Try to plot this motion out on a position versus time graph, okay? And compare your answers to each other, help each other out if you're like, what's a graph again? Help each other out,